Okay, folks, learning goal 7. We're going to get real weird now talking about superpositions, basis sets, and expectation values. This will probably be another pretty heavy one, but we can do it. So let's find it way down here. Let's go for it. So there's going to be a couple consequences that we need to go through based on some of the things that we've just discussed. So let's recall some of our solutions that we've come up with. So we came up with this solution for our 1D time-independent translational motion Schrodinger equation. When we applied the linear momentum operator, we came up with the following: px operating on psi plus, and I really should back up and just say I'm going to call this whole chunk psi plus, and this whole chunk psi minus, just to make the equation a little bit easier to write. And so when we operated on psi plus, we got plus kh bar as our linear momentum. And when we operated on psi minus, we got minus kh bar. And if we were to invoke that A and B are both necessary, in the past we said, we'll call one 0, call the other 0. And we did that just to make the math a little bit more easy to follow. But now technically, when you think about this, if we have both of these terms in this linear combination, we have eigenvalues corresponding to a state of definite but different momentum, right? We have momentum in the positive direction, and we have momentum in the negative dimension, okay? And remember, that was a result of this cosine linear combination, as well as the sine linear combination. So because of this, we say that the cosine function, and we could also say the same about the sine function, is a superposition of two individual wave functions. So this linear combination that we've been exploring, we call that the superposition. So if we think about this more conceptually, back to our wave function here, we could think of the psi plus state as particles with linear momentum plus kh bar. And so on this space right here, that means plus kh bar would describe particles moving in this direction. At the same time, we also have this psi minus state available, and that describes particles with linear momentum in the negative direction. And in this two-dimensional graph, right, that would mean particles moving to the left. Okay. And what you notice here is in this situation, they both converge and end up in some middle area right there. And if we recall what we discovered with curvature and kinetic energy, right, we can see their curvature is quite small. So they have low kinetic energy on this side, and their kinetic energy is increasing as we go this way. And similarly, their kinetic energy is increasing as we go this way, to where we end up at this singular point right here, where now they have zero kinetic energy. So we're on the verge of something really cool right here. And so what this implies is, in a large number of measurements, there will be an equal probability of finding particles moving left and finding particles moving right. And that will coalesce into finding them in some most probable position given by this peak. So to describe this, we need a linear combination like we have here. We call that linear combination a basis set. And the more terms we have in our basis set, the more we can describe the physical properties of our particle with as much accuracy and precision as possible. So here is just a simplified way of looking at that linear combination, right? A wave function is a superposition of more than one wave function, and therefore all wave functions must be described by a basis set. So that basis set is given by this linear combination, right? Some summation where we have some unique constant, some weighting normalization constant in front of each wave function. So in a single observation, one eigenvalue corresponding to one value at psi at that superposition will be found. We'll show on the next slide the probability of finding that eigenvalue is proportional to the square modulus of the normalization constant, right? I'll just say norm. And finally, the average of a large number of observations is given by the expectation value of the operator. That is this equation right here, the operator sandwich. So I'm going to demonstrate that with my Mathematica model right here. As you can see, I've got a sum of cosine functions, and I've set this up in a manipulate where as I increase this value of n, I'll be increasing the number of terms in my basis set. And so you can see with one singular cosine function, I get this ordinary, regular old wave function, but there's no difference in its momentum or kinetic energy due to the curvature, right? So now when I add another term in my basis set, something cool happens. I got this juxtaposition of interfering construction and destructive interference, constructive interference and destructive interference. And now as I add more and more and more terms in my basis set, I am getting this coalescing of a superposition. I'm getting the particles to appear sharply in one definite spot. And as you might imagine now, if we look at the kinetic energy to do this curvature, they are accelerating from left to right and from right to left and meeting somewhere in the middle. So that's pretty cool. To go further down the rabbit hole with this proof, okay, we can show that any one measurement is going to correspond to the weight of that measurement, okay? So for example, if I put all of this together now, so let's plug in psi into these two terms here, okay? So I get the following. I get that this is going to be C1 psi 1 plus C2 psi 2, and that's all complex conjugate. And then I've got my operator sandwich, right? And now that's C1 psi 1 plus C2 psi 2 d tau. And this, after we carry out this operation, should all give me a real eigenvalue. And in this case, due to this operation, we would call this eigenvalue the expectation value, the result of a large number of observations. Okay? So this is going to get pretty heavy, so let's follow through it. So first, the operator operates on psi. And when that happens, right, when omega operates on C1 psi 1, right, I'll remind you, right, omega operating on psi gives me little omega operating on psi. Okay, so I'm going to keep all of this here on the left for now. Okay, and then I'll just plug that in directly. So now what we end up with is C1 little omega psi 1 plus C2 little omega psi 2 d tau. And then now, as you might note here, we need to FOIL this thing and pull things out of the integrand that are a constant, okay? So just checking my place to make sure I'm on the right track. And then I also need to apply that complex conjugate through all of these terms, right? So if I FOIL this thing first, okay, so that's going to be C1 star, right, from there, times C1 times little omega. Oops, that's a psi. We need there to be a little omega. Okay, beautiful. And then now, let's see here. That becomes integral of psi 1 star psi d tau. And we're going to, obviously do this integration by parts. So that was my first. So now I've got to do my outside. So that's going to be C1 psi 1 times C2 omega psi 2. So now what I'm going to get from that is C1 star C2 little omega. And then now that's going to be times psi 1 star times psi 2 d tau. Okay, beautiful. So that was my outside. Now I need to do my inside, which is going to be these two terms. and then now that's plus, and we're going to have C2 star times C1, just regular C1, right, times little omega, and now integral of psi 2 star times psi 1 d tau. And finally, we can do our last term, the C2s times the C2s. So that's going to be C2 star times C2 times little omega. And I realized I should probably indicate that that's 1 and that's 2. So let's make sure that I've got all of that in there. So that one should be 1. Let's see. First, outside, that one was number 2. Inside, that was omega 1. And then now last, that's omega 2, okay? And then now finally, that's the integral of psi 2 star, psi 2 d tau. Goodness me, what do we have here? We got a mess. Well, in fact, we don't, because we can take advantage of two of our properties. Differing states are orthogonal. The same states are normalized. So where we see a psi 1 star and a psi 1 star, that's going to survive. Where we see a psi 1 and a psi 2, those are differing states, so they have to drop out to 0. So let's drop all those terms out to 0. So this whole chunk becomes 0. And this whole chunk becomes 0. And now what I'm left with is the following. C1 star C1 is just the square modulus of C1, right? Times little omega 1. And then now, because these are normalized, we know psi 1 star psi 1 just becomes 1. Or we're going to rather impose that they're normalized. So this whole chunk dropped out to 0. Great. This whole chunk dropped out to 0. And then now we've got plus C2 star C2 is just the square modulus of that term, beautiful, times omega 2. And then now, because we've imposed that these two same wave functions are normalized, that just becomes 1. And thus, we have the following equation, okay? And all of that equals the expectation value. So I'm going to box this off and note that now our total expectation value is some linear combination of, in this case, only 2 results, but you might imagine we could add, you know, in this case, I did like 63 of them over here, right? We could imagine 63 terms. Our expectation value is an average of all of those different results. And if we want to know the operator, or the eigenvalue, I should say, so the omega of any one of those individual results, that is proportional to the square modulus of that normalization constant. Beautiful. Okay, we have solved the crisis. And as it turns out, this result, as confusing as it might be, leads into a very famous result. And we'll talk about that in the next video.